Hi, and thank you for attending the last session. So I'm sure you're very courageous to stay till the end of the conference. Doesn't show very well, but it's supposed to be the zeroing picture that initiated this famous meme, but it's okay, you can guess what it is. So this is what we're going to cover today. It's a 30-minute talk. I'll try to leave some room for questions, and this is what we're going to address. So basically, I'm going to introduce myself very quickly. I'll recap what root means on on an Android devices, and we did a very lightweight reverse engineering, and we'll go through the toolbox we use to do that research, and we'll present our findings and a little tool that we built for to help us analyze these applications. So this is a joint paper between me and my two other colleagues at Symantec Research Labs. We've been involved mostly in academic conference, so it's our first publication at Black Hat. And we're involved in cloud security, binary, dynamic analysis, static analysis, and all the good things. That's what we do in our daily work. So the context of this presentation is how many of you are using personal devices for corporate usage? Wow, less than I expected. But it seems to be a very big trend, especially on iOS, and especially on Android. iOS is still not the first citizen corporate environment, but it's going there. And if you look at the market research, that's not my number. They say that about 70% of the devices are running Android. So that's kind of a big market to address. And somehow root has a bad reputation. And if you've read the news, I think it was 2 weeks ago or last week, Lookout published something about new malware that were leveraging root exploits to, insert themselves so deep in the system that one of the recommendations was buy a new device, which I thought was pretty funny. So root has a bad reputation for, valid reasons. And when we started to look at it, we asked ourselves these questions. So what does it, how many applications actually check for root? Of course, you have, Candy Crush maybe, or, other types of games that are worried that you're going to hack their in-app purchases, and probably not the most interesting use case for us, because we wanted to see, we thought that the guys best position to address and look for root traces on a phone would be security vendors. And in case you're not aware, we are a security vendor as well, a small one. And we wanted to see how good these checks were. And after that, we wanted to see, okay, now that we know how these checks work, how easy is it to subvert these checks and to make an application believe that your device is not rooted while it in fact is? And the way we looked at it, we wanted to compare security vendors. So think about AV solutions. And most of these vendors, they also provide a bring your own device solution that is the corporate version or the enterprise. And we wanted to compare these two products, ideally from the same company, and see if they do the same thing, they have the same concerns, or if they do something more complicated on one end. And of course, we're very curious to see how people were doing it. So the way we started this work is we looked at our own product, the consumer product, and we saw the checks they were doing. We were a bit surprised, and we decided to check the state of the industry. We were wondering if we were only the bad student or if everybody was doing the same. Luckily for us, you'll see that we're not doing so bad. So a rooted device, if you guys are Windows user, it's the administrator. It stands for super user. And the way it works on Android, so if you have your Linux system, you just invoke the super user binary, you get your prompt with a sharp, and then you can go crazy from there. On Android, slightly different. So first of all, you need to root your device. That process basically means you're going to have an exploit. This exploit is going to basically drop a super user binary compiled for your architecture, put it at the right place, or export it in your path environment variable so that you can access it from anywhere. And the way you invoke it is it's tied to a root management application. It's a 6-step process. That's a pretty complex process to execute a command as a root user on Android. So basically, you have an application that invokes the super user binary. And the super user binary basically will send a root request intent, because on Android, everything is intent. That's basically glorified IPC communication. And the root management application is going to register a broadcast receiver for this root intent, and then is going to verify a policy whether you allow this application to execute a command as a root user. And then it's going to tell you yes or no. And in the end, the command is going to be forwarded to a su daemon, and this daemon executes the command for you and returns back the results. The last part, the su daemon, is something new that has been introduced for rooted devices after, I think, KitKat or 4.1 or 4.4. But anyway, so that's basically how rooted devices, and if you want to execute a root command, that's how it works. So before we go a little bit, to the results, we have to go quickly over what's an application. Of course, we didn't have access to the source code of all the security vendors besides ours, and we decided to basically pull application from the Android marketplace and look at it. So doing some reverse engineering. And luckily for us, Android is very easy to reverse. So you have several layers, but basically it's Java-based. It's compiled into a set of classes, and you have resources. And all the classes get packaged into a DEX format that gets interpreted by a Dalvik VM, and it's basically stored into this APK container that is, again, a glorified zip format. You can just unzip it, and you can see the content of the file. And the analogy, if you're running iOS, that would be an IPA file. So the good thing is that if you guys have, Java has been there for a long time, and there's a lot of tools that can be reused on Java bytecode. And the way Android builds it, they basically change a little bit the semantic of the bytecode, and it allows us to reuse most of the existing tools for Java. So that's when you unzip an application for an Android, that's what you get. And if you so you have the manifest file, you have the classes that it's a package, contains all the set of classes that are going to be used by the application. You have the resources. Think about the application needs to run on multiple screen, multiple resolution, so everything will be stored in there. And then you have a bunch of signatures and hashes to make sure that the integrity of the application is still maintained when you install and execute it. And sometimes you will see this lib folder. So this lib folder is, instead of using Java, you'll use some compile code. That would be native code, C, C++, and that will be in there. And you can have several folders for different architectures that the application is supposed to support. So I just want to stress that it's not rocket science. So these are the tools that we use for our investigation. And so the first one converts the Android bytecode to another format that is the Java archive format. The reason we do that is to be able to leverage the second tool that is JD Core, that basically recovers this Java archive format, basically bytecode into source code. And that's the good thing. Java is decompilable to some extent, unless you do some strange manipulation. But in cases where we couldn't recover the full source code, we basically use APK tool. And APK tool gives you this intermediate format that is Smally, which is assembly for Java. Very high-level assembly, but you can play with register, load values, and all the good stuff you do with assembly. And of course, we are very lazy. We want the computer to work for us, so we build a lot of glue code. So these are the custom scripts that do all the processing for us. So now we're going to go into the results of our analysis. So we pulled a bunch of APK. We're going to go through all the applications that we downloaded and the vendors we looked at. So the first one is presents a file. If you remember what I told you, is that basically when you're a super user, when your device is rooted, you will have the super user binary somewhere. And some people realize that, most exploits like towel root and all the big exploits, they basically just dump the super user binary into system bin or X bin, and that's where it is. And some people actually just look whether the binary is in there, and they issue an open or a stat command, and they assume that your device is rooted. Obviously, you just move the binary somewhere else, and that's it. Your device is not rooted. Some people realize that there are some smart people out there that would use dynamic path. So if you're under normal operating system, you'll have an environment, you will have a set of environment variable that you can call from anywhere, during your current path. And this is what these guys are doing. They basically check all the environment variable in your system, and they iterate over each of these paths, and they append the / super user. And for each of these paths, they check whether you have the super user binary. Again, it's a very naive way to use it, because you could just not export the super user binary because you don't feel like you need it every time, everywhere from, everywhere in your system, and you could just invoke it with the full path yourself. And that's what these guys are actually checking for. Some people went the lazy route. They assume that it's a Linux system, so you have this wonderful which command that basically tells you which binary you're actually running by returning you the full path. If you guys have used Python and you didn't use, the way to Python env to manage your environment, you've used which a lot of time to differentiate between Python 2.7 and 3.x. And some people were even, they went even simpler. They basically just run the super user binary, and they check the return code of the sub-process. So if it was able to run, then they assume that your device is rooted. And again, this is the same as checking if it's in the environment variable. And some people realize that if you go back again to the first picture, that to have a device rooted, in general, you would need a root management application. And they're actually checking for one. Some of them are checking for super user APK, and they're checking if you have that, you're definitely rooted, which is, again, a very invalid check, because any of you, without having your device rooted, can absolutely install this application. You could download it. You're not going to do anything with it, but you're going to have it. And they will detect that your device is rooted. So some people, they're checking for binaries with the set bit UID, which, again, you can have binaries that have this bit set, but that doesn't mean your device is rooted. You could have it for very other reasons, but again, doesn't mean your device is rooted. And some people, they check, so the first one to check for the root management applications, they're doing it by looking at the path. And some people are using the API. So Android, the SDK provides you an API that you can call, and this API can return you the set of the packages that you have installed on your system. And they check if you have one of them, you're definitely rooted, which again is not true. And some people, they're even, on Android, you can execute shell commands, and you have these PM list packages that will, if you run the terminal, you SSH to your phone, you can run that, and it tells you the list of applications that you have installed. And that's how some people are doing it. That's what we call general device settings. Some people are verifying what test keys or what keys you have in your environment. So in Android, you have a bunch of strings, like the kernel version, the kernel name, and all of that. And people are checking whether you have these test keys. And if you have these test keys, you're potentially rooted. But again, if you have release key, you could have a release key yourself. If you build your own version of Android, you could have release keys, and you could have the super user binary in there. Doesn't mean you're not rooted. So again, these are very flaky checks that these people are doing. And you have another bunch of strings that you can get from Android, specifically the version of the OS that you have. And if you have custom ROMs, if you've installed Cyanogen, people are checking basically the checks that we've encountered in the wild. They were checking only for the presence of this specific fork of Android. So that's slightly more interesting, because now we've encountered all of these were pretty easy checks and nothing really rocket science. Some people are doing something slightly smarter. And if you remember, when you root your device, you need to drop the binary somewhere. And the preferred path to put it would be in system or system bin. So for that to happen, your exploit need to be able to mount the partition as read-write, drop the binary in there, and usually they will return back the permission to read-only. But some people figured that sometimes you may have the partition as mounted as read-write. Again, from my experience, it's not really a very good check. And some people, they don't even check the results of the mount. Some people check the result of the mount command. Some people just try to create a file in there just to see if it, if it works. And if it works, obviously you have access to the system partition, and obviously that's an indication of a rooted device. Another checks that we've encountered was the check for the user ID. So under Linux, everything is, so you have a user ID. The user ID, the lower, the more privileged. And obviously, people were checking if you had the user ID 0. Android has a very complicated execution process. So if you want to run an application on the command line by yourself, you have like zillions of arguments to be able to launch the Zygote. The Zygote is going to instantiate the process. You have the app process. So, and basically, every time you run an application, it gets a new user ID, a randomized user ID. That is never close to 0, even if you're rooted. So, again, it's a very curious check. And I must admit that I've only played with Android 4 and above. So maybe in Gingerbread that was a thing. I doubt, but maybe. So anyway, this is pretty much the checks that we've encountered. And all of that without doing any dynamic analysis. So all of that was doing static analysis, pulling the APKs, decompiling, doing some smart search for a bunch of strings that would be in there. Fun fact, most of them are not obfuscated or very lightly. So now, these are the results of, this is where the industry stands these days. I'm not going to speak for, I'm not going to bash much the other companies, but speaking for ourselves, we were very surprised that we were just checking for the super user binary in a very specific path. So at least we got one check. So the number on the column in there doesn't represent the number of checks exactly. It's the number of type of checks. So we're doing only one type of check, checking if the binary is in a specific folder. And this is for the consumer versions of these products. So I don't know. You can see that some people, some companies, they don't bother to check. They assume that, who cares? If you're rooted, you probably wanted it, so it's not very important. And I have to say that some people are doing a better job than others. Kaspersky, for example, were checking for, they were checking very thoroughly what people were doing. And anyway, so, but there was the interesting bit, I think, is here, is that there was there's a company that decided that, you know what, you're rooted, we may as well give you new features. And Avast actually leverages the root feature to provide you a personal firewall. So if you install it on your phone, you can have the firewall. And the way it works, if you guys have tried to build a VPN, a firewall on Android, it's pretty nasty. So you have to bind, your own VPN interface, redirect all the traffic to this local VPN interface, and you have to have the mapping with the process, process ID and socket file descriptors, and then you need to recraft the IP headers. And if you're rooted, you just have an IP table. So now I understand why they do it. It's pretty easy. It saves your life. We were very disappointed because nobody was using native code for root detection. Nobody in the consumer versions of their product. And there are frameworks out there called root clock, and I think under the hood it's using exposed. And basically this application allows you to cloak the state of your device, to pretend that your device is not rooted. And all the application out there, you could run root clock and pretend that your device was not rooted. So the interesting thing with Kaspersky checks were that they were actually doing, we had to review the results manually because they were using reflection. So we had to dig a little bit deeper to identify what kind of checks they were doing. So, and then when we saw that, we're pretty disappointed, and we figured, nah, that must be the consumer version. There's no money to make there. So people are actually, focusing on the very hard problem of protecting corporate data. Not really. So if you look at the results, you still have providers of bring your own device solutions that do not check whether your device is rooted at all. So that's pretty scary. If you think about you having your corporate email, your device is rooted, whether you chose to root your device or not, but you cannot ensure integrity of something that is on a device and you don't even check for that. So some solution would basically check if your device is rooted and then boot you out of the network or won't allow you to connect to a VPN. And so again, pretty disappointing results for the whole industry. And us, don't worry, I'll have some self-introspection, and we're doing also the same check. We're doing the exact same check on the consumer version and the enterprise version. Nothing really stand out in there except IBM. IBM were doing very, very good checks. They're checking for every possible cases. However, they were doing in almost clear text. They were doing it in Java. So you can have great detection mechanism, but if anybody can reverse it, then it's not that good. So we found two companies that were actually using native code. So AirWatch was using, they had their MDM agent, and if you open, if you decompile the application and if you unpack it, you could see that there was a shared object, an ARM shared object in the one we looked at. However, there's no string obfuscation, there's no packing, there's not even like integrity checking on the binary itself. So you could just snap some sections and the binary would run fine. And the bulk of the checks were in the get device state method that gets reported back to the mothership, I assume. And again, very easy to reverse. The other one was Exciter. They had a library as well. Very easy. You open the binary in IDA or Opera, and then in like 5 minutes you can identify the check. 4 vendors had no checks. Okay. There's only one where it's controversial because I've been on their website and they claim they do have a way to check for jailbroken devices, which I assume they would do also for Android, for rooted devices. Is that the way these solutions work is that they have a backend that the administrator provision with a set of policies, and maybe there's a way to provision a policy where you could blacklist binaries or indicator of compromise. Again, IBM did a very good job, but no obfuscation at all, even on the Java, no native code, so fairly trivial to recover the content. So, as I told you, we did most of that statically, but except for Kaspersky, where we had to actually look why some files were, we didn't see what we expected. So we basically needed a tool to do some dynamic analysis, and we use this tool in in another context. So we build a tool that's basically you build a library, you inject it, and if you think about Linux, that's how it works. You can inject a library, and the symbol that is in this library will be called first before going to libc. So if you think about printf gets fetched into libc, and then in our case, we LD preload it. That allows our symbol to be first, and then we could hook printf and other bunch of functions. So the way it works, on Android, you don't do LD preload. As I told you, to launch an application, it's a bit of a nightmare to do it manually. So you have this set of set properties, set prop, and you can set properties for different packages. And here, we basically set the property to have LD preload on our application that runs our shared object built for the platform. And again, library hooking is fairly easy. So basically, you have a pointer to the real function that is stored in libc. And then you create your own implementation, you do what you want, and then you either return the results of your implementation, or you can return the result and call actually the real implementation in libc. And here, we did something very simple. We check if open concerns the super user binary, and if it tries to open it, we say no, it doesn't exist. Believe it or not, that's very simple, but that can defeat a lot of checks. Again, we use this tool for a different purpose, and just to show you that in case you're interested, library hooking is still alive. It's an old technique, but it's still working on Android, and you can have fun. We came across, not in this project, across binary that are doing self-protection, verifying if they're not being traced or being debugged or modified. So the way you do it, at least the ones we've encountered in the wild, again, they basically try to check if the process is being traced. And the way it is on Linux, you can basically, each process expose some information like memory pages, memory allocation, stack, values. And then you have this trace repeat value that tells you the PID of the process that is tracing you. Obviously, you want to see 0, so that means nobody is tracing you. So what we need to do, because it's a, we need to identify the file descriptor of the status file for your process. And then every time we encounter a call or an open call for this file descriptor, we basically override the value of the trace repeat to 0 to say that, no, that process is fine. It's not being traced. So this is the conclusion. I'll leave room for some question, but that was pretty sad for us, and that's why hence the title of the presentation. But really, it seems like the whole industry is doing a poor job at verifying whether a device is rooted, and it's a very big concern. So some people had no checks on their consumer version, but they had a check on their enterprise version. Symantec and Kaspersky, we had the exact same checks, but I think Kaspersky had a different build system because which is oddly enough, in the consumer version, they used reflection. They unpacked this DEX file on the fly at runtime, and it was already unpacked on the enterprise version. So probably a different build system or something, or somebody screwed up at some point. Some other company, they had absolutely no root checks. And most of the solutions that we've seen out there, they're vulnerable to root cloak and the exposed framework. And of course, we benchmark our solution, our small tool, and because our tool is native and root cloak basically is at the middleware level, so it injects jar classes and hook these functions. But as soon as you do a GNI, a native interface call, basically you cannot interpose on that. So our tool does it at a lower level, hence the results. Okay, now you have to believe me that we learned a lot from that investigation, and obviously we stepped up our game and we made a lot of improvement in our root detection. If you don't believe me, in a few months you can download the new consumer version of one of our product, and obviously the checks are going to be much better. But on top of that, instead of just doing the checks natively, that is making the reverser life a little bit harder, you still need to do some binary hardening. So if you do packing, unless you're using a very known packer like UPX and everybody can just click a button and unpack it, that's making it a little bit harder. If you do string encryption, again, the number of people that can do it, it's much harder. And if you do software self-checksumming, it's still, I think there's some research that prove that it's defeatable, but it's pretty hard, and it's CPU specific, because it needs to, it's playing with a TLB cache and shadow pages. Anyway, so we did a good job. We improved our solutions, and hopefully, we hope that the whole industry is going to do a better job at protecting their customers, because that's scary. And I run a rooted device as well, so I feel concerned. And we actually did the same kind of investigation using machine learning. So because our solution that sits on your phone collects data and send it back, we actually explore a new way, basically just analyzing the data to identify with a set of features. We have about 70 features, and we're using ensemble machine learning, and we're able to detect that a device is rooted or not. We're publishing that work. And maybe TrustZone is another way to go forward, because even though you have software self-checksumming, you're still running on an untrusted platform. And ARM provides you a way to basically run things into a secure environment. Think about TPM for mobile. So with that, I'm done. And if you guys have any questions, go ahead. Yes?
So at least for custom ROMs, using only user mode, even if it's native code, using only user mode code for detection, isn't it a pretty lost battle? Because if I make a custom ROM, I can make a custom kernel, the USS, and you can even put your own infrastructure of managing root, not just a typical super user APK. You can do pretty much everything.
Oh, I agree with you, but if it's the problem of running an untrusted platform, right? If I own the kernel, that's I agree with you. It's a very tough game. That's why I think there might be solutions with TrustZone, and we looked into it, but the API and the limitation of TrustZone makes it harder. I think TrustZone needs to provide a wider API, and maybe we can do something. But I really believe that having a secure component is the way to ensure maximum integrity. Because currently, I agree with you. It's going to be workaround. It's going to make it harder, but there's no solution. Yeah. One more question? Yeah. Yeah.
What would be your recommendations for implementing this correctly?
We have it. We did a lot of it, but I don't think we can disclose it right now because it's IP.
So I'll have to reverse your app and find out.
You can try.
Thanks.
Thanks. Any other questions? Thanks.